When you think about math, it's easy to picture it as this ancient field where all the big stuff happened hundreds of years ago. Well, I'm here to tell you that's just not the case. We are living in an absolutely incredible golden age of mathematics, a time when these super abstract ideas are literally unlocking the keys to our future. So, yeah, let's get into it.
Okay, to give you a feel for what I'm talking about, let's kick things off with a classic, a puzzle that has been stumping mathematicians for 200 years. It's called the moving sofa problem, and it's actually a pretty simple question on the surface. What's the biggest possible 2D shape, our sofa, that you can wiggle around a 90-degree corner in a hallway?
For a long time, the best guess we had was this funky shape somebody came up with back in 1992. But proving it was the absolute biggest, that seemed next to impossible. And then, bam! 2024 rolls around, and a new paper drops that finally settles it. Turns out that 1992 shape is the one. A problem that's been on the books for 200 years just got solved.
But hey, this golden age isn't just about solving these kind of quirky, fun puzzles. Let's talk about something called Bragain's slicing conjecture. Now, this is a seriously tough problem in what's known as high-dimensional geometry, which, is basically the study of shapes with way more than the 3 dimensions we live in. For geometers, this has been a massive focus for years, trying to get a handle on the properties of these mind-bending forms.
And yep, you guessed it, a proof for this conjecture also landed in late 2024. The math community online, especially on places like Reddit, they just lit up. They were calling it a huge deal for convex geometers. And that's the point, right? This amazing momentum, this feeling that these huge, long-standing questions are just falling one after another. That's what makes this a new golden age.
Okay, so we've seen a couple of quick hits. Now I want to slow down and really dive deep into one of the most profound breakthroughs of the year, a discovery that's helping us decode the hidden structure of the mathematical universe itself.
Yeah, we are talking about the proof of the geometric Langlands conjecture. And look, this isn't just a single result. This is the culmination of decades of work by a whole team of mathematicians. It's a genuine intellectual epic, and what it does is build a bridge between entirely different mathematical worlds.
So, what exactly is the Langlands program? Well, the best way to think about it is like this. Imagine you find 2 ancient, completely alien texts. They look totally unrelated. The Langlands program is like the search for a Rosetta Stone, a key that proves they're secretly telling the exact same story, just in 2 different languages. It's trying to connect the universe of numbers with the universe of shapes.
And I love this quote here from mathematician David Benz-V. He describes it as this epic journey, like Odysseus trying to sail between 2 great perils, the whirlpool of physics on one side and the monster of number theory on the other. It just perfectly captures the sheer ambition and, honestly, the guts of this whole project.
So, building a bridge, what does that actually mean? Let's get a little more concrete about what kind of dictionary these mathematicians are trying to write. Okay, so on one side of our dictionary, you've got number theory. This is the world of arithmetic, the study of distinct, separate things like prime numbers. And then on the other side, you've got geometry, the study of continuous forms, shapes, spaces, and all their symmetries. On the surface, they couldn't seem more different, right? Like oil and water. But this new dictionary is showing us they are fundamentally linked. And this quote just nails it. It's called the Knots and Primes Dictionary because it reveals this mind-blowing analogy that prime numbers behave in ways that are strangely similar to physical knots in a 3-dimensional object. It's like finding a hidden symmetry woven into the very fabric of reality. Unraveling one helps you understand the other. Okay, so this is where you might be thinking, that's cool and all, but it's super abstract. Why should any of this matter to me? And that is the crucial question, because the answer is a huge, emphatic yes. This is where the story pivots from the purely theoretical to something incredibly futuristic.
All right, let's talk applications, because it turns out that understanding these deep geometric truths is becoming a revolutionary tool for engineering things we honestly thought were pure science fiction.
Take another recent breakthrough, the proof of the MNOP conjecture. Now, without getting too deep in the weeds, what it proves is that 2 totally different ways of counting the number of curves you can draw in a complex 3D shape secretly give you the same answer. It's a really deep insight into the fundamental structure of 3D space.
So what's the big deal? Well, here it is. That exact kind of deep, abstract geometric insight is what AI algorithms are now using to design a whole new class of materials called metamaterials. And these things have properties that can seem to just break the normal rules of physics.
So what are metamaterials? Imagine a material whose superpower doesn't come from what it's made of, like steel or plastic, but from its incredibly intricate geometric design. We're talking about things that can bend light to create an invisibility cloak or manipulate sound in ways we've never seen in nature. Their power is pure geometry, and that's exactly why these mathematical breakthroughs are so important.
And this is just the start. This new level of geometric control is pushing us towards the ultimate frontier, manufacturing things not just with fancy patterns, but literally atom by individual atom.
Some researchers, like Jennifer Hoffman, are pioneering what you could basically call quantum 3D printing. The idea is to lay down single atomic layers, then use a tiny probe to arrange each atom exactly where you want it, and then stack those layers up to build a 3D object from the ground up. It is an incredibly high-risk, high-reward mission to build the quantum devices of the future.
And that brings us to the final piece of the puzzle, and maybe the most profound application of this mathematical golden age: building the computers that are going to define the next 100 years.
You know how our current computers work, right? They use bits, which are either on or off, a 1 or a 0. Simple. Quantum computers, though, use qubits, and a qubit can be a 1, a 0, or, crazy enough, both at the same time. And that unlocks a level of computational power that is just almost impossible to imagine.
But here's the kicker: the connection back to our math story. Building a stable quantum computer that doesn't constantly make errors is an enormous challenge. And it turns out that the very same kind of complex, high-dimensional geometry that's being explored in things like the Langlands program is essential for building the theoretical backbone for these machines. The math isn't just some neat analogy, it is literally the blueprint for making fault-tolerant quantum computers a reality. So, as you can see, this is about so much more than just solving old math problems. It's about forging brand new tools that let us see and build the world in a fundamentally new way. Okay, let's tie this all together. What's the big takeaway here? We are in a golden age of math. These abstract proofs we've been talking about are like finding a new Rosetta Stone, revealing these hidden connections between totally different fields. And this isn't just academic. These connections are the direct foundation for future technologies, powering everything from AI-designed materials all the way to atomic-scale manufacturing and, of course, quantum computing.
And that leaves us with one final incredible thought. These new mathematical tools are letting us see hidden connections between worlds we never knew were related. So the question is, what other invisible structures that govern our reality will they allow us to see and build next?